Okay, in this video I want to look at a polyprotic acid. Specifically, I'm going to look at sulfuric acid. And by polyprotic, I mean one that has more than one hydrogen that are available to donate. Typically with these acids, the first proton process is strong, and then subsequent proton processes don't tend to be as strong. So H2SO4 is going to completely disassociate from H3O plus and HSO4 minus, but then the HSO4 minus can react with water again to produce SO4 2 minus and more hydronium, but this process tends to be weak. What I want to do is I want to figure out what my pH is after the first proton process, and I want to compare it to what my pH is after the second proton process and see if I think it's worth doing multiple proton processes when determining the pH of a polyprotic of an acid with more than one hydrogen. So first of all, if I have 0.02 molar of this, the strong acid process is easy. It says that I'm going to produce 0.02 molar of this, and that's going to happen to completion. So I don't have to do any of my typical equilibrium. That means that if I want the pH of this, I can do negative log the concentration of hydronium and get my pH to be 1.7 essentially, based on the first proton process. Now, assuming that first proton process occurs to completion, let's look at what happens in the second proton process. So here, I'm going to have 0.2 molar, let's try that again. Erase. If this process goes to completion, I made 0.02 molar of this in my initial situation. This is a liquid, so I'm not paying attention to him. And I don't have any of this yet, but I've also created 0.02 molar of this at equilibrium. Because I have a 0 here, when considering this change, it's still going to have the reaction going to the right because I have to produce something here at equilibrium. It can't be a 0. So the equilibrium has to shift in this direction. And then at the equilibrium situation, plus x there, I'm going to have 0.0, that's my change, 0.02 minus x. I'm going to have x, and I'm going to have 0.02 plus x. And if I look in the book here, I can see the Ka for this process is 1.0 times 10 to the negative 2. So, writing my equilibrium expression, Ka is going to be equal to the concentration of SO4 2 minus H3O plus. Everybody's in a 1-to-1 ratio here, so I don't have to do anything funny with exponents or anything, which is nice. And on the bottom, I'll have the concentration of my HSO4 minus. So 1.0 times 10 to the negative 2 is going to be, I'm just going to change that. It's easier to think of that as 0.01. It'll make my life a little easier. This new concentration is x. This is 0.02 plus x. And this will be 0.02 minus x. So it's going to be a quadratic. I'm going to do a little solving here, but 0.0002 when I multiply those together, minus 0.01x when I bring this binomial up to this side, equals 0.02x plus x squared. And now bringing everybody to the right, I'm going to get 0 equals x squared. I'll bring my leading term up front, plus 0.03x minus 0.0002. Now I'm going to use my calculator to solve this quadratic for me so I don't have to do it myself. Oh, I don't have that kind of calculator. Just a second here. Alright, this one will do it. Okay. Okay. So my A value is 1. My B value is 0.03. My C value is negative decimal 0.0002. And I get 5.6 times 10 to the negative 3. And a negative 0.0356. X cannot be a negative because we can't have a negative concentration on the sulfate ion. So this is not possible. So this is our solution. And now let's go and adjust our hydronium calculation to reflect this change. So it was 0.02 concentration of hydronium was 0.02 plus X, and that will work out to be 0.02 plus 0.0056, and it becomes 0.0256. So it's a slight change due to the secondary proton process, but not a huge one. The resulting pH then is negative log 0.0256, which will be log 0.0256, which is 1.59. So with the first proton process, I got a pH of 1.7. With the second pH process, I got a little bit more hydronium and my pH lowered to 1.59. So I guess the question is that enough of a difference to make it worthwhile to consider the second proton process when calculating the pH for this acid? And the only answer I can really give to that for you is it depends how accurate your pH needs to be. If it needs to be really, really accurate, then you should include it. And if it doesn't need to be that accurate, it's probably not that important. You can see it's only a small change to the concentration that happens because of the second proton process, but it's not an insignificant amount of change.